Hi everyone, and welcome to the second of 4 videos going through some past exam paper questions on the topic of the equilibrium constant, Kc. And the first question we've got this time, again, is exactly about Kc. It's asking us to write the equilibrium constant expression. So remember, when you're writing your Kc expression, it's always products over reactants, and we need to use the square brackets to represent concentration. So it'll be concentration of CO2 and concentration of N2 on the top. But remember, we need to raise them to the power of how many moles are in the equation. So the CO2 concentration needs to be squared. The N2 concentration can just stay to the power of 1 because you've only got 1 mole of it. And then we're dividing by the concentrations of the reactants. So we need concentration of CO to the power of 2 and concentration of NO also to the power of 2. What are the units of this equilibrium constant? Well, we don't really need to work this all out. We can do a bit of a shorthand here. We're going to substitute in moles per decimeter cubed wherever we've got a concentration. And you can see that in total, we've got a power of 3 on the top and we've got a power of 4 on the bottom. So essentially, this is going to come out as moles per decimeter cubed to the power of -1. Because we're going to have moles per decimeter cubed to the power of 3 divided by moles per decimeter cubed to the power of 4. But we can't leave it like this. We need to sort this out. Okay, that's going to come out as moles to the -1, decimeters to the +3. And then that would be fine, but the standard way of writing it is to write it with the positive power first. So decimeters cubed per mole. Then we have the calculation. We've got a 4-mark calculation here. These are fairly standard. We're going to, again, go through our ICE table. This method is really nice. You know what to expect, and you can work your way through this method kind of methodically. So let's write our equation out. And we can start constructing our table here. What do we have initially? How does it change? What do we have at equilibrium? Okay, what information do we have from the question? It says we've mixed 0.46 moles of CO, so that's how much we had at the start, with 0.45 moles of the NO. Mixture is left to reach equilibrium. They analyse the equilibrium mixture and finds that 0.25 moles of NO remains. So when it's come to equilibrium, we've got 0.25 moles of NO left. Just be really careful that you add these numbers in the correct places. If I put this here, for example, it's going to mess things up later on. So just be really careful, making sure you've got things in the right places. The total volume is 1 decimeter cubed. That's going to make things nice and easy later on. Okay, well, if we started with 0.45 here and we ended up with 0.25, then we've gone down by 0.2, haven't we? And because we've got a 2-to-2 ratio here, we should also be going down by the same amount here. They're going to react in the same ratio. Just be careful that you make sure you're applying the ratio to the changes, okay, not to the initial amounts or to the equilibrium amounts. Okay, it won't be a 2-to-2 ratio here. It will be a 2-to-2 ratio here in the change because they react in a 2-to-2 ratio. So if we take that away, we're going to end up with 0.26 here. It didn't tell us how much of these we had initially, so we have to assume that we had none. Okay, that's usually the case. Okay, they'll tell you otherwise. And so again, we're now going to apply the ratio. We've got a 2-to-2-to-2 ratio, so it should be the same value, but because it's a product, it's going to be plus 0.2. We can't go any lower than 0, can we? So we're going to end up with 0.2 moles at equilibrium. But here we need to be careful because it's 2-to-2-to-2 to 1, so this is only going to be plus 0.1. Remember that we can't then take these values and put them straight in here. We need to convert them into concentrations first. Okay. So to convert to concentration, we need to do the moles divided by the volume. But in this case, the volume is 1 decimeter cubed. So we're just going to divide all these values by 1. So actually, they're going to be the same values. Okay. We're just going to divide by 1 and so on. So actually, we can just put these numbers straight in here. So let's calculate it. CO2 squared, just be careful again getting the right numbers in the right places. So CO2 is 0.2 squared times 0.1. And then on the bottom, we want 0.26 squared times 0.25 squared. Right, let's just work this out. 0.2 squared times 0.1. 4 times 10 to the minus 3 times 0.25 squared. Okay, this is going to be very close, right? You can see this is going to be nearly 1, isn't it? It's always worth thinking about roughly what is this going to come out as. These two are very similar. So it's going to be slightly less than 1, isn't it? Okay. Yeah, does it tell you how many significant figures we need to do it to? No, it doesn't mention it. So if they don't mention it in the question, they can't mark you down. I'm just going to call this 0.95. Okay. This question then continues, and it then asks us, what does your value of Kc suggest about the position of equilibrium? Okay. Well, our value of Kc was 0.95, which is less than 1. Remember, if the value of the equilibrium constant comes out as exactly 1, then it's telling you that you're exactly halfway between the reactants and the products. Okay. So the fact that it's come out as slightly less than 1 means that our equilibrium position is slightly to the left. We're slightly towards the reactants. Okay. So we can say, it's only a 1-mark question, so we can say the position of equilibrium is slightly to the left because Kc is less than 1. Okay, it then says the chemist increases both the temperature and the pressure of the equilibrium mixture, and it's left to reach equilibrium again. What is the effect, if any, on the value of Kc? Okay, now this seems, I think, a 1-mark question. We've got to consider 2 different things here. It seems a bit mean, but the catch here, remember, is equilibrium constants are only affected by temperature. So straight away we can say changing the pressure is not going to affect the value of the equilibrium constant. Okay. So all we need to do really is work out what effect the temperature is going to have. So what are they doing? They've increased the temperature. So if we increase the temperature, according to Le Chatelier's principle, the position of equilibrium is going to shift to counteract that change, to decrease the temperature again. In order to decrease the temperature, it's going to shift in the endothermic direction. So if we go back and look at our reaction, it's telling us that delta H is negative, so that's telling us that it's exothermic forwards. So we said it's going to shift in the endothermic direction, so it's going to shift to the left. If the position of equilibrium shifts to the left, it means we're going to get more reactants and less products. And so therefore the value of Kc is going to decrease. So that's what we need to say. We need to say that Kc will decrease, and then we can say the position of equilibrium will shift to the left. Because the forwards reaction is endothermic. Sorry, the forward reaction is exothermic, isn't it? And it's shifting left because it's shifting in the endothermic direction. So the forward reaction is exothermic. Just check, is that right? Yeah, the forward reaction is exothermic. Now, part 2 then is actually quite interesting. So it's saying, explain why it's difficult to predict what would happen to the position of equilibrium. So actually, what we've said here is not necessarily correct. Okay, we probably should actually cross this out. Okay, Kc will decrease. The forward reaction is exothermic. That is true, but the position of equilibrium is not actually that straightforward. Okay, because although the pressure is not going to affect the value of Kc, it is going to cause the position of equilibrium to shift. Okay. We've already answered half this question, right, with the temperature change. So we can say increasing the temperature shifts the equilibrium to the left. We already explained that. And actually, it should go in this question rather than there. Okay, what's going to happen if we increase the pressure? Well, if we increase the pressure, the equilibrium is going to shift to decrease the pressure, and so therefore it's going to shift to the side with fewer molecules of gas. So if we go back to our equation, which side has fewer molecules of gas? The right-hand side. Okay, that makes sense. That's why it's going to be difficult to predict. Okay, increasing the temperature shifts the position of equilibrium to the left. Increasing the pressure shifts the position of equilibrium to the right. Because the right-hand side has fewer molecules of gas. We need to put that explanation in. We don't actually need to explain the temperature bit because we've already explained it up here about the forward reaction being exothermic. And then we just need to write a sentence here to explain why that makes it difficult to predict. The idea is that because one factor is shifting it to the left, the other factor is shifting it to the right, it's difficult to predict the relative importance of those two things. Okay? Which of these is going to be more important? Well, we don't know without any more information. Okay? And that's why it's difficult to predict. Okay? It's difficult to predict the relative importance of these two factors. And they do like you to have a sentence that says something like that. It doesn't need to be worded exactly like that, but something that gets across the idea of, I don't know which of these two effects is going to be more important.